process heat integration in design project for the final year student. So let me share. Okay, so this is the disclaimer. So, so I got this from myself, my own experience, not from someone else's. So and then I think because we only have like 1 hour, right? I will skip some topics. This is not going to be like a detailed talk on heat integration because the detailed one we will need another 1 semester for that. And then the second disclaimer is that the tool itself is not that important. Yeah, the most important part is that understanding the process as we go later on with the case, and then once we understand the process, we know what to do, and then there comes along with the tool and the software. So understanding the problem and then the skill on the process engineering is really the key in this topic. I divide the presentation into 2 things. Let's see if we can catch up, but I will maybe I will skip some slides. So the first part will be integration, heat integration in practices. If you can see my mouse, there's a pointer. So I will share some examples that I've done before, so that it will give some ideas for the others, so that they know what we can do with that. And then how we can implement some of the concepts in the undergraduate design projects. Yeah. So some resources that we typically use is number 1 is this book from Prof. Robin Smith from University of Manchester. So it's a very good book. So I recommend to read this chemical process design and integration book from cover to cover. Very easy to read. You can also use it as a pillow if you want. It's very thick as well. The second one, which also a book that I recommend for final year students, also like graduate students, young engineers. So this chemical engineering design from Tauler and Synod. This book used to be the sixth book. I mean, because they are like Coulson and Richardson chemical engineering book. There are 6 parts. So this is the 6th part for the chemical engineering design. So they rename it in this manner. And then you can also read the 2nd edition of book from INChem, Pinch Analysis and Process Integration, where you can also Google IChemE Excel spreadsheet for the tool as a companion of this book. And then there are also like a commercial software tool from Aspen HYSYS, like this one, Aspen, I think it's Aspen Energy Analyzer. And then there's also another software from KBC. So people from the University of Manchester, from the place of Robin Smith, and then INChem, they I think they spin off a company, or they make this like a super target, and also this but this company is now Linhof Marsh was the name of the company, and then they are now owned by KBC. So they have this a nicer version of heat exchanger network tool. Just to share some stories, experience that we have here locally in Malaysia. If you are interested to read more details, just go to this Chemical Engineering Transaction Journal. The title is that Pinch Analysis Applications for Foul Crude Distillation and Condensate Fractionation Units of a Refinery. So this is a case study that we did some years ago in a refinery in Malaysia. So I cannot name the refinery, but I think you can guess which refinery that is. So the process is as follows. So we have a crude feed, right, coming from the tankages. It is pumped through a series of heat exchangers, what we call like a CDU preheat train. So CDU means like a crude distillation unit. So we have a main crude fractionator over here, the CDU, and then upstream of that CDU we will have a series of heat exchanger which are used to recover heat from the distillation column. Why they need to do so? Number 1 is to recover the heat as much as possible. That's the main goal. And then there are some separations over here. It goes to some units, some stabilizers, splitter, and so on and so forth. And then there is also another fractionation unit. They call it condensate fractionation unit, CFU. So this C is condensate, while the C is crude. The difference is that condensate comes from, we typically say condensate if the feed is like coming from the gas wells. So gas, once we separate the gas from the heavies we typically name them as condensates. So this then condensate feed, while the crude is then coming, just simply crude oil coming from the oil platforms. So this one comes from the like oil wells. This guy comes from the gas processing plant, and the gas comes from gas wells. Yeah, so this as the same setup, we have the distillation units over here, and then we have a series of heat exchangers as well. So this is in one complex of a refinery, and then this is another complex in the refinery, and then they are separated by think about quite a distance, not short, but quite a distance. So the first thing that we did is we do a kind of like a mass balance reconciliation, because in the plants there are some streams that we don't know what the flow rates are, and also we don't know what the temperature coming in and temperature out, going into and going out from heat exchangers. So we need to do some mass balance reconciliations. So for that we need to model the whole plant. Like in this case, we model that in a process simulation software, and then by doing so we can then extract. So we model this. I mean, like you guys now are doing, you are modeling your final year design project, right? So you model that, and then from this model, from the mass and energy balance, we extract the flow rates, we extract the heat capacity, and then we extract the temperature in and out for each of the heat exchangers. While in this case, in practice, we have several design cases. I think in your undergraduate project, you only have like one case typically. So we have like a design case, and then some light case, and then heavy case. So this is then the total energy that is required as the fired heaters for this CDU and then CFU. So the total energy externally, yeah. So if we say total energy externally, that means coming from the fired heaters, typically where we burn fuel. Okay. So it's about this 90 megawatt of energy. And then we this is a bar charts of representations of these numbers, and then we once we get the mass and energy balance reconciled, we develop something that I think you know already, the grid diagram. So the grid diagram, so we see it on the right over here. So this grid diagram, we have like hot streams coming. So we typically draw it like so my way of drawing this is that we read from left to right, right? So the lower temperature should be from the left side, and then the higher temperature from the right side. So if a stream needs to be heated up, that means it's a cold stream. So that means the arrow will then be moving from left to right. So like this one, see, for example, this number 35 degrees C, it is then moving towards to the right up until 148 degrees C. So this is a cold stream. Okay, and then a hot stream is the other way around. So it is moving from right to left, the higher temperature to the lower temperature, like in this case, from right to left. So from 136 degrees C, it goes to 109 degrees C. So this is a hot stream, this is a hot stream, this is a hot stream. So all of these streams pointing to the left are the hot streams, streams pointing to the right are cold streams, right? And I also typically put like in one complex, this is the CDU complex, this guy over here, and then the CFU is below here. So I separate them into two so that we know, psychologically or feeling wise, we know that these two are like a different complexes, and then there should be some distances between them. And then I also place like hot streams on the top part. Like for example, in this case, these streams are the hot streams, while these streams are the cold streams. So this is the cold streams of the CDU, This is the hot streams of CFU. This is then the cold streams of CFU, sorry. Yeah, so as you can see. So once we get this basic of this grid diagram, we can then place existing heat exchangers. Like in this case, the white one. This is the existing heat exchangers. So these streams, so we have one big streams over here. It splits into three, and then one of the one part is then matched with the streams somewhere here. So this is an existing match of heat exchanger, and then we can then put the numbers next to it. So it's heating up the stream 175 until 178 degrees C with this 3 kilowatt per Kelvin, the MCP. And then this is the name of the heat exchanger, and then this is then the load of the exchanger, about 1 megawatt. Yeah, so that's how we draw this. And then typically we draw like a heater, like a red circles. This is then the furnace for the crude CDU. This is then the furnace for the CFU. All the blues are the coolers, so either cooling water or air cooler. Okay. And then we did also some analysis on the current performance. Say, for example, the ones in greens, existing heat exchangers that we see that we need to clean them. So how do we know that? Because we have some readings on the field where we plot the. Let me draw just to give you an idea. Yeah. And so we plot. So we plot. This is then time. This is then we calculate the Q, because in a heat exchanger, if you know the flow rate, you know the CP from the mass balance. Okay, I need to go back. This happens always. 1 second, give me some time. I think I will do it this way, which is easier and safer. 1 second, yeah. Yeah. No. Okay. So we plot in time, and then we have the Q, and then we have we have the data of flow rates, and then CP from either the data sheets of the heat exchangers or from our mass balance reconciliations. And then once we know the flow rate, CP, and then temperature in and out, we can calculate the Q. Yeah? And then from this Q, we can simply plot something like that. Yeah, depending on the data that you have. But this is then the typical like heat exchange for each of the heat exchangers. And then we can see at the time we had like three cycles of cleaning, three cleaning cycles, I mean 3 turnaround periods of data. It was like I think it's more, at least 6 years or even 9 years, I don't remember. But then we see this. So something like that, and then this then one cycle, and then this is another cycle, and then we have the third one. And then we can see the typical performance of each of these exchanger, and we can say that if one exchanger is then moving towards in this area, because then the heat exchange is very low, that means probably the fouling in the exchanges is very big already. That means we need to clean this particular heat exchanger. So that's roughly how we identify this whole green heat exchanger. And then we did some analysis on some exchanges as well, and then we can see, for example, this type of notation that we make. We say that this is a particular heat exchanger that can be enlarged in such a way that we can maximize the heat recovery. So this heat exchanger, that heat exchanger, which is then corresponds to these streams. Okay, so this is then the type of analysis that we do when we did this project. Okay, obviously when we did this, we spent some time, and then there are many slides and many calculations behind it, which I don't put on in. I cannot put them in one slide. Yeah, but if you're interested to read more, you can go. You can just simply Google this article. Okay. See, 1 second. Some technical issue. Okay. Yeah. Okay. This is another chemical plant, heat exchanger debottlenecking, heat exchanger network debottlenecking at the time. Basically, we use the same approach. And then if you want to read more on this, you can go to this link of the article. And then I will skip some of this. This is another chemical plant in China at the time where we wanted to increase the capacity by doubling the capacity of this particular plant. And then at the time we say, well, if we increase the capacity, that means, if you can recall, let me put this. So if you can recall, we will go through this, but I hope you get already some ideas on this. This is what we call a composite curve. For one plant, the temperature profile is this is the temperature profile, right? So temperature, this is then the heat profile, and then if we double the plant, the temperature profile will be the same, right? I mean, if we want to increase the temperature from 30 to 100, if the capacity is double, the temperature profile is still then the same, right? It's still the same, 30 to 100. But then by doubling the plant, that means we are increasing this guy by roughly 2 times as well. Yeah, by roughly 2 times as well. So if we have this type of profile, this A megawatt, for example, and if we double the plant, most likely we will have 2 A's, right? So we have like something like this for the hot stream, and then we may have something like okay, this is a holiday mode. So and then assuming that you are now seeing like a blue color, so this is then hot composite curve, it is then the cold composite curve, and then this number will be roughly 2A, roughly. Yeah, if we double the capacity double. So then we don't want that, obviously. So we were thinking at the time how to reduce this 2A to something much less than 2A, right? So that's why we did this heat integration project at that time. And then by the end of the study, before means the base case, we double the capacity, we calculate the heat energy balance, and then we get this targeting 38 megawatts and then 49 megawatt for the cooling tower. And after we do the heat integrations, instead of 38, we down to 36.3. So it's only like 2 megawatts, right? It's only like 2 megawatt difference. But then the prices of the steams, because there are 3 different headers for the steam: high pressure header, mid pressure header, and then low pressure header, and then the price are different. So we could then at the time save quite significant amount of money per year for this after this exercise. Okay, now okay, we have another. Now, we have seen what we can do in practice. The same thing that you can do as well in your final year design project, right? So we're just here to recap a little bit. Yeah, I think most of you know this already. When do we do this heat integration analysis? So when we first well, either it is in practice, like in real life, or it is in your undergraduate study. The steps are about the same. It's about the same step. So we design from the reaction, from the reaction sets. We then design the reactor, and then from that reactor we design some separation and recycle system. So we follow this onion diagram, and then once we design the separation and recycle system, that means we have the whole flow sheet like this. Right, so we have reactor 1, reactor 2. So for example, here we have the feed coming in, and then we need to increase the feed temperature to a certain degree C, and then we put them to reactor 1 and then reactor 2, and then we do some separations, and then unreacted is then sent back to the reactors. Products is then sent to somewhere. So that's basically the simple case. So once we get this, we get the separation and recycle system. We then see what we can do to recover the energy as much as possible, right? So once we can then see how much energy is being recovered, we can then design the heating and cooling utilities, and then the water and effluent treatment. So that's basically the steps. So the powerful nature of this pinch analysis or heat integration is that we can know what the target is, means how much is then the minimum energy that we can that we have to fulfill. Minimum energy that we have to fulfill into the plant, as in how much fuel that we have to supply, and then how much heat that we have to discharge to the environment, as in the cooling tower. Right? So how much is then the minimum of these two, without knowing what the detailed design looks like. So that's the powerful information that we can obtain from this pinch analysis. And then once we get the targets, we can then move on through this grid diagram, design the heat exchanger network, to really go into details on how to design the heat exchanger itself to maximize the heat recovery. So that's basically the same the approach. So if I make it to like a step by step. So number one, once we get the mass and energy balance reconciled or developed, we identify which are the hot streams, which are the cold streams. So I think by now you know already, hot streams are the streams to be reduced in temperature, and then cold streams are the streams that need to be heated. So hot streams to be cooled down, cold streams to be heated up. And then we select a temperature mean, the delta T mean. So this is like an arbitrary number, like an average delta T across the plant, in such a way that we use it as a guideline to design the heat exchangers. Say for example, we select delta T of 20 degrees C, for example, and then from this delta T we construct the composite curve, and then the grand composite curve, and then from these curves we get the minimum energy target, as in how much heat utility, and then how much cold utility, and how much then.
Dr. Zulfan, I think something wrong. I can't hear you.
You cannot hear me.
Okay, now okay.
Okay, sorry, yeah. When did you lose me? Just now.
Just now.
Okay.
Just a few seconds ago.
Oh, okay. Good. Thank you. So I will repeat this. So we once we get our mass energy balance reconciled, we identify the hot and cold streams. So hot streams means streams that we need to reduce their temperatures, we need to cool down, and then cold streams are the streams that we need to heat up. Yeah. And then we select any arbitrary delta T mean as like an average delta T, across the plants that we are going to use to design heat exchangers. And then once we get that, we design or we calculate the composite curves for the heat and cold, and then also for the grand composite curve. So you learn in the class how to construct this, but there are now software or Excel files that you can find online on how to automatically calculate this for you. Yeah, I just give you an idea. And then we know from these curves, we know the energy targets that we can supply to the plants, as in then how much is then the minimum hot utility, and then minimum cold utility, and then how much is then the heat recovery that we can do in the plant. And then from these graphs, as I will show you later on, you can then use these graphs to identify any feasible process modifications. So once you identify a feasible process modifications, you can then try to modify it, but then you have to go back to this step, because then once we identified any process modifications, the streams, they can change. Yeah, either the flow rates can change, or the temperature in and out can change, so anything can change. So we can then see the targets, and then if it's feasible, and then we can use that process modification, so we can apply it. If it's not feasible, that means we can just remove or discard that option. And then the second option is then we can also integrate with other process equipment. Say for example, if you have you can integrate, like if you have like two distillation column, for example, and then one is then operating at higher pressure, the other one is operating at lower pressure, and then you can then integrate the condenser and reboiler between them in such a way that you can always minimize the energy supply into the system. So that's an example. And then once you do that, we can then use some cost estimation tool to estimate the whole heat exchanger network for the capital cost, and also for the operating costs coming from the fuels and then the cooling tower. And then we record that number. Yeah, so for this specific delta T min, we record the capex and opex, and then you can then vary another delta T min, for example, if you want. So for the first step, you can start with delta T min of 20, and then later on you can do another delta T min of 10 degrees C, and then calculate again the capex and opex. And then another step, you can then use like delta T min of 30, and then calculate the capex and opex. And then from these three data points, you can then roughly gauge where the optimum delta T min is. And then once we get that, you can then design your heat exchanger network. So that's basically well, theoretically speaking, and practically speaking, how we do things. It's just a matter of how accurate the cost estimation is, and then how accurate is the yeah, I mean, how rigorous you want to do this, right? Because in a project you have a timeline. Say for example, in our refinery example, this one, so we only select like one delta T at a time, because we have the existing plants, right? When we do the mass energy balance reconciliations, we calculated the delta T for each of the heat exchangers, right? Existing heat exchangers. And then the delta T varies a lot, from 5 degrees C until 30, 40, 50 degrees C. And then we just simply take the average, and then we use that average as our design delta T. We don't go into the details on comparing the capex and opex for each of the delta T, because that is not really practical. Number one, not practical because we don't have like integrated cost estimation at the time. So that's one. Number two is that well, it's project, it has a certain time duration, so we need to move on fast. But nonetheless, that's the concept in it. So in doing so, this is like a freshman. Yeah, there are three important equations that I can share with you. Number one is that MCP delta T. So we apply this MCP delta T for both hot streams and then cold streams. Again, hot streams are the streams that need to be cooled down. Cold streams are the streams that need to be heated up. And then heat transfer can only occur from higher temperature region to the lower temperature region. So from like this, yeah. So this is then the heat transfer. And then we typically have like y-axis as temperature, and then x-axis as the Q, or the enthalpy. And then another equation is that we have the heat exchanger equation itself. The Q equals to UA delta T LMTD. Yeah. So we have MCP delta T for hot stream, MCP delta T for cold streams. Hopefully they are the same. And then how much is then the heat exchange between the streams, which is governed by UA delta T LMTD. And the delta T LMTD itself is this number, is this formula. So you don't need to memorize this. So basically, what you could do is let me sorry, right. So this is your so this is your delta T1. So for each of the heat exchanger, you can simply draw this, and then this is your delta T2, right? So you have T1, delta T1, delta T2, and then you can then say, okay, delta T LMTD divide, and then delta T1 minus delta T2 ln delta T1 divided by delta T2. As easy as this. So this 1, 1, 2, 2, right? That's it. So if you say that this is your 1 and this is your 2, so then it's the same basically. Either way, it's fine because negative will cancel out each other. But then what's more important is that it has to be consistent. I think I'm getting into the same error again if I write down something. Well, one second. In any case, I have to minimize this writing. Sorry, we just walk step by step. Yeah. If there's any question, just let me know. Otherwise, I will just go step by step. These steps, maybe some of you may know this already, but nonetheless, say for example in this case, just to give you some confirmation. So we have I put here stream 3 for example. Yeah, now you can use this stream 1 as well, but nonetheless, so we have a stream coming in at 80 degrees C, and then it needs to be heated up to 140 degrees C. So we can say, well, 80 to 140 is then the inlet and outlet temperature. So 80 to 140, and then we know from the mass balance the CP is then 4 kilowatt per degree C. So it's 4 over here, and then the delta enthalpy is 240. So 240. So we do this for all streams that needs to be heated up and cooled down. And this particular stream, for example, needs to be heated up. So that means this is then cold streams. So we have cold streams for stream number 3, and then another cold streams, this cold streams from 20 until 135 as stream number 1 cold streams. And then we do the same thing for the hot streams. And then this is then the basic of this cold the composite curves. Say for example, for the cold composite curve, we have stream number 3 and stream number 1, which I just mentioned. So 20 to 135, and then 80 to 140. And then they have like this then the enthalpy for stream 1, enthalpy for stream 3. For this interval 20 to 80, the CP is 2 because there's only one stream 1 in this interval. So we put it there from 20 to 80 with the same slope, yeah, CP of 2. But in this interval 80 to 135, we have two streams, stream number 1 and then stream number 3. So from in this interval we have to sum all of this CP. So CP2 plus CP4, that means we will have like CP2 plus 4, which is 6. Yeah, 6. So this is then the sum. This CP is 6. Yeah, it is MCP. And then lastly from 135 to 140, that's the CP number 4. Okay. And then the summation is this one. So we have from here to there, that's 120 you can recall. So we have MCP times delta T, you get the Q, right? And then this is another MCP, which is 2 plus 4, 6 already, times the delta T is then this number, 110 plus 210, 220, 220, which is 330. And then there's another 20 kilowatt over here. And then the same way we design for the hot composite curve, right? This is how you do it manually. But then if you use software, you can just simply enter the stream flow rate and then the CP and then temperature in and out, and then you will get your composite curve like this with a specified delta T. So this curve was created with delta T of 20 degrees C, and then you can see why it says 20 degrees C, because the minimum distance between these two curves along the regions of this heat load is 20 degrees C. That's the minimum distance, which is somewhere here. You can see this is sent from 80 degrees C to 100 degrees C. The minimum distance is 20 degrees C, while other areas, they are most likely, or we can see them, they are bigger than 20 degrees C. If we go up and we go down, they are all bigger than 20 degrees C. The difference between the hot streams and the cold streams. So this is then the region, the pinch region, what they call it. So this is then the minimum delta T that we allow, minimum delta T that we allow for the heat to transfer in this plant, right? These are like design delta T. So with this selected delta T of 20 degrees C, we have the temperature pinch of 90 degrees C, somewhere in the middle, 180. So in between is then 90, sorry. And then this area, the non-overlapping area on the top, is what we know as the minimum heating utility, which is in this case 65 kilowatts. And then the area over here where the heat streams are not covered by the cold streams, so this heat needs to be discharged somewhere, so eventually it goes to the cooling utility of 105 kilowatts. And then while the area in between hot and cold streams, the overlapping area over here, they are the heat recovered zone. So this is then the amount of heat that can be recovered. Okay, so that's the composite curve. But then what if we increase the delta T by another 10, for example, from 20 degrees C to 30 degrees C? So that means we are moving this blue line to the right. We're moving this blue line to the right because we start at heat load of 0, so we cannot move this hot stream. It has to start with 0. You can move along, we can move everything to the right, but then for simplicity, we can just fix this hot composite curve on the 0 axis of the heat load as anchor. And then if we increase the temperature delta T mean, or reduce the delta T mean, we can simply move this blue line to the right and then to the left. And then you will see, if we move it to the right, you can imagine, if we move it to the right, you can imagine that the overlapping area becomes reduced, while the non-overlapping area, for example in this heating utility, will become larger. So if we move this blue line to the right, that means we will then increase the minimum heating utility. We will reduce the heat recovered, but then we will have like a smaller heat exchanger, right? Because we increase the delta T. Similarly, if we move it to the left, which means we reduce the delta T, that means we will then reduce the heating utility, we will increase the heat recovery, and then we have to increase the heat exchanger area. So that's basically what we can read from these graphs. This is what I just said. So we have like, if we have like a different scenarios of not only the delta T but different cases, depending on your mass and energy balances. You can have like a plant with no heating utility, or another plant with no cooling utility. Maybe you can have like a plant with then more than one pinch point, so you have another pinch point over here and then another one over there. And then we could also have like cold utility at the higher temperature and another cold utility at the lower temperature, something like this. And then and vice versa, you can have like a hot utility at lower temperature and another hot utility at higher temperature. So you can see these kinds of scenarios. Yeah. So this is then how we create the composite curve, and then you can wonder, well, they call it pinch analysis, and then why we don't see any pinch. So pinch is that this is the minimum delta T. So the pinch point is the 90 degrees C. So how do we get to this 90 degrees C? We have a method called like this, a shifted temperature. So we shift the temperature of hot streams down by half delta T. We shift it down by half delta T, which is in this case 10, yeah, because the delta T, the selected delta T is 20, so shifted by half of it is 10. So this whole red graph will be reduced by 10 degrees C. And then similarly, the cold composite curves will be increased by another half delta T. So it will then increase by another 10. So this will then increase by 10, and then we have the two graphs pinch at this, they meet at this 90 degrees C. So by adjusting this temperature, we make sure that there always be delta T between them. Yeah. This is how it looks like. So this, we have the original data, like in this case 20 to 135. You can, if you can still recall the number, and then once we adjust the temperature, yeah, we use like for example 20 degrees C. So this guy, because it is a cold streams, we increase the stream, yeah, this one, because it's cold streams, so we increase this by another half. So 20 plus 10 becomes 30, 135 plus 10 becomes 145. So that's the temperature that we adjust. But the flow is still the same, right? It's same flow rate, same CP. The same goes with the hot stream. We reduce it by another half, which is 10. So 170 minus 10 is 160. 60 minus 10 is 50 with the same MCP. And then if we put them into this interval temperatures, so we have this original data. The highest is 170, the lowest is 20 degrees C. So we plot them in the ascending order, and we plot the corresponding streams. We get this type of graph. And then with the shifted temperature or the adjusted temperature, we use the adjusted temperature obviously. So maximum 160 degrees C, which is this guy, and then minimum is 20 degrees C, which is that guy. And then we put this. So stream 2, for example, this stream 2, which is this one, 160 to 50. So 160 to 50, right? So when we know in this interval 160 to 150, there's only one stream whose MCP is 3, yeah, this guy. And then but then from this interval 145 to 150 or 150 to 145, we have two streams. So this stream number 2 and then stream number 3, and then the MCP is then obviously this is 3 minus 4, which is minus 1. So that's the net MCP, 3 minus 4, and so on and so forth. So with that, you can then calculate the whole MCP. This is then the minus 1 that I mentioned, and then you can then see, you can calculate 10 by 3 is 30, 5 by minus 1 is minus 5, and so on and so forth. And then you can then make a cascade. Yeah, all of this will be done for you in the software. This is to let you know the basic behind it. So by the end of the day, this is then the cascading. So we have in this interval 160 to 150, we have a surplus of 30, put it 30. We have no external heat, right? We have no external heat. And then in this interval we are minus 5, so minus 5, so 30 minus 5 is 25, and so on and so forth, until we will see the lowest temperature, which is minus 65. So if we use this number as a external heat supply, that means we put this 65 over there as an external heat, and then you can then use the same delta enthalpy in each interval. So 65 plus 30, 95, 95 minus 5 is 90, and so on and so forth. And then you can then see in this interval at shifted temperature of 90 degrees C, which is the pinch point, you get the cumulative enthalpy of 0. Yeah, so this is then your pinch point. So this will lead to, if you plot this, this heat with this temperature 160 65, 150 95, you will get what we call grand composite curve, like this one. So 160 we have 65, 150 we have 95, see, and so on and so forth. And then at 90 degrees C, you have 0, which is this guy, right? So this is what we call grand composite curve. And then the associated cold composite curve is basically this one, right? Like I mentioned to you, the hot streams reduced by 1 delta T, half of delta T. The cold streams increase by half delta T as well. So you get your pinch temperature over here. So this is what we, yeah, and then you can see the pinch temperature visibly. So what's the use of this grand composite curve basically? One second, yeah, I need to move because my battery is about running out. One second, yeah. Okay. Can you still hear me? I hope so.
Yes, we can hear you.
Okay. Yeah. So what's the importance of this grand composite curve? The importance is that we can design various utility system. Say for example, the easiest one. Is that we typically assign, so we have to supply a hot utility at 160 degrees C, yeah, the adjusted temperature. So that means the actual temperature should be, because it is hot stream, has to be like a 170 degrees C, yeah, delta T plus 2 plus half of delta T. And then we need to supply the minimum cooling utility from this to that temperature. Say for example, we need to supply the chilled water from 5 to minus 5 to 15 degrees C. So that's one option. And then another option is that if we see this graph, we don't need to supply it at 160 degrees C. We can supply it at 140 degrees C, for example, right? Because if we have utilities which cost differently at different temperature, we may need to strategize a little bit so that we can maximize utilities with the cheapest price first, right? So in this case, you can say, well, utility at 140 degrees C somehow cheaper than utility at 160 degrees C. So instead of using this utility, we can use this utility, right? And then well, I cannot have like a huge chilled water, for example. I can only have like this amount of chilled water, because chilled water you need to have an extra power for to run it. And then the bulk of the cooling utility will be run by cooling tower, so you have the cooling water. So this one is cheaper compared to this option. And then you could also say, well, yeah, um, one second, why is this the same with that? I don't remember. But nonetheless, we have a third option. Why do I have the same number? Um, yeah, okay. We have the third option, which is then I can have another a cheaper utility at 120 degrees C over here, combined with this 140 degrees C utility. See, the total duty is the same, 65 kilowatt, but then the steam header, for example, or the type of hot utilities are different because they are of different prices. So we can maximize it in this manner. The same goes with the cooling utility. So we can say, well, I'm going to use chilled water in this region, cold water over here for the cooling water. This one I can use it to make a shower for hot water, right? Then you have a hot shower in the in your plant, in that sense. So right? I mean, if you can use this hot water, you can, because it's a 90 degrees C up until 70 degrees C, so which is quite hot. So you can then design the utilities in such a way from looking into the grand composite curve. So that's the powerful nature of the grand composite curve. Now, what is the process modification? This is what they call like I think I mentioned this already, the importance of pinch point. This is like the bottleneck of the process. What we could do here is, if you can see this minimum heating utility, it is there because there is no hot stream above these cold streams, right? There is no hot streams above these cold streams. That means if we can then shift some of the process streams in such a way that you can move some portions of this up the pinch point, so that this guy can be, it can cover more of this blue region, right? So if we can move some of these streams over there, then you can then reduce the heating utility and reduce the cooling utility, because you are moving some parts in this region, right? The other way around is that we have this hot utility because we have too much of these cold streams on this side. So if we can then modify the process in such a way that we can reduce this guy, we put it below the pinch in such a way that it can cover a little bit more in this region. That means we can then reduce simultaneously the hot utility and the cold utility. Yeah, so that's what they call like a plus and minus principle. So how do we do that typically? So this is how we do it. So we can then play around with the reactor conversion. So depending on where you are in the company or which company you are working with, if you're working in a licensor company, companies that own the technology or develop the technology, yes, this is then one of your options where you can then play around with the reactor conversions, operating conditions. But then in most cases, majority will not be working for licenses. They're not designing process from scratch. Other options that we can do is then we can play around with the distillation pressure. So the examples that I did, well, this guy, we in fact, well, not we, because I'm no longer in as part of there, but then they are licensors. They own the technology, and at that time they could not change the reactor conversions because it's already there, but they can shift some of the steam pressure. They can shift some of the steam pressure in such a way. Some columns, there's one big column over here that consumes huge amount of energy, but then apparently when they reduce the pressure a little bit, they can then move that column from the medium pressure range to lower pressure range. So that means they can reduce then the steam consumption from the high pressure, because there is this what we call it like what do they call it? Yeah, I don't remember. It's what is, I mean, if this region needs more heat, we can open this. I don't remember what this valve is called now, because it's because I don't deal with this anymore. But nonetheless, that's how they do that. So if we put some of this guy over there, that means this can be then closed, so we're not consuming a higher amount of high pressure steam, and then at that time, these low steam header, we have another source. So that source is much cheaper, and then we can then save some money with that. So that's what we did. We changed the pressure of the column. Where is that stuff? So you can do that as well in your PDP. You can also see if you can change the preflux ratio and then how much it will then save your energy. Yeah, we can also do some pump around, like in the case of that this guy. Yeah, all of these preheat trains, they are recovering heat from pump around systems in the CDU, and then CFU, right? So we take some heat from this, we take some streams out of these columns, and then we cool it down by heating up the feed, and then we pump it back to the system, to the plant. So that's what we call like a pump around. And then we have feed vaporizer. Say for example this feed vaporizer as well. It's more like it works with the pump with the with the heat exchanger network. So assume that if we don't have any of this feed preheat train, and then the feed will then be still in liquid, and then in this fire heater of the CDU, it will have to supply a lot more energy to vaporize the feed. But if we have all of these heat exchangers, we'll have a feed partially vaporized already, which can then reduce the load of our fire heater, or the external utility as we call it. Evaporator pressure, you can also control it and then reduce it. Heat pumps, it's also the same thing. Yeah, I don't know if you know heat pumps. So heat pumps is more like if we see this graph, so you have this heat somewhere here, right, which you can then extract, and then you can pump it up. Yeah, so you can compress it in such a way that it can condense above the pinch. Yeah, so you normally see this in a propane propylene splitter. Yeah, propane propylene splitter. We don't have time to explain what that is, but then it's you can Google this. In propane propylene splitter, they have this heat pump where they pump heat from one lower pressure to higher pressure, which they can then condense. There's also not some options that you can another options to shift any streams to be below and above the pinch. Now last part is then heat exchanger network. So once we do some modifications, I think in this example, the original the original hot utility was 65, and then once we did some examples in the class at the time, so we came up with 15 kilowatt for the heating utility, and then still 105 cooling utility kilowatt for cooling utility. So at least we reduced the hot utility. So once we fix this some process modification, we design the heat exchanger network accordingly. So there are these pinch golden rules, which I think you know already. If not, these are the pinch rules. So there should be no heat transfer across pinch. So heat from this region, from this stream, cannot be transferred above the pinch, because if you take this out, one second. Yeah, if you take this out, that means this stream, yeah, say for example this stream, yeah, this is a bit difficult to explain in this with using this graph, but then if you can imagine, if I take these streams above, that means this guy below, it needs to have some external heat to heat, right? So if we move this above pinch, that means yes, it can cover this maybe, yeah, depending on the temperature, but then it will leave this guy blank. So we still need to supply the heat on this in this region. So that is then the first golden rule. And the second one is that we should not put any cooler above pinch. So above pinch is the area where we have to maximize the use of hot streams. Yeah, so that means we cannot cool this down with the cooler. So we need to maximize the heat in the above pinch. And then similarly in the below pinch, we cannot use heater. So that means all of these blue lines, the cold streams, it needs to be used as much as possible to cool down the hot streams. If we use heater here to heat them, that means some portions of these hot streams will not be cooled down by the cold streams. Instead, it will go to the cooling tower. So we will then have a bigger cooling tower in that aspect. These are some of the rules to understand. We will then have to start from the most constrained point, this pinch point. So that means this is the pinch point. Yeah, remember the pinch point is like 90 degrees C. So the hot stream's pinch point is then the 90 plus 10, which is the 100 degrees C. So this is the hot stream. Hot streams, the pinch point is 100 degrees C, and then the cold streams, the pinch point is then the 90 minus 10, which is the 80 degrees C. So remember, when we can do this adjusted temperature to see the pinch point, or to design the grind composite curve, but then when we design the heat exchanger network, we will have to put it back to the original temperature. We have to put it back to the original temperature, as in this case. So you can see then the hot pinch temperature 100 degrees C, and then the cold pinch temperature the 80 degrees C, as in the this guy. So the hot pinch temperature is 100 degrees C, the cold pinch temperature is the 80 degrees C. So this is where we have to start. This is where we have to use the start using the heat exchanger network design. Now we start at the most constrained point, because this is then our the minimum delta T that we allow, right? 20 degrees C among the streams. If you say, for example, if I draw, I think I have to draw in paint. If I say, make it easier. 1 second, yeah. I have 4 minutes left, but I think it's important. There are many things that you don't have to memorize. Say this then your pinch, right? This then your hot stream, this then your cold streams, and then the slope is then the I think I missed this, but the slope is then MCP, right? Because the y-axis is always temperature, and then the x-axis is always Q. Yeah, so if we divide delta T divided by Q, you'll get 1 over MCP. Yeah, can you imagine? So Q equals to MCP delta T. So delta T divided by Q, you get 1 over MCP. And then this slope is basically this guy. So 1 over MCP. So you have 1 over MCP. So if we have a bigger streams, that means a bigger CP or bigger flow rate, that means the slope will be smaller. Yeah, the slope, if we have a bigger MCP, that means the whole thing will be lower. That means the stream will be a bit shallower. Can you imagine? So this MCP is bigger than that MCP. So if this is then the most constrained point, this is something that you cannot change, but then this temperature, this region and that region, it can always change, right? So you can recover this heat, for example, as much as possible, in such a way that all of the energy can move to these streams. But then you have to pick this stream in such a way that when you put the energy, its temperature doesn't go up like that. Yeah, because this is then going to be the violation, because we have the delta T very small. Delta T is smaller than this delta T. This is the smallest delta T that we allow. The delta T means 20 degrees C. So we have to select a cold stream whose MCP is larger than the hot stream, right? So that's one rule. And then the other rule is that the other way around. So if we have these cold streams, we have that hot stream. This is fixed, and then you have to select a hot stream that has to have MCP larger than the cold streams. Yeah, this MCP hot has to be larger MCP cold. Otherwise, this guy will be something like that, which we don't want, because this is then violating the system. So that's basically the concept between that. It's something that you don't have to memorize. It is here, that one, but I skip it. So when we obey that rule, yeah, so above pinch, we will have to select the MCP of the cold bigger than MCP of the hot. So that means this is hot stream, this is cold streams. The only match is that this hot stream can be matched with that one, right? 1.5 and 2, and then this stream can be matched with that one, and then below pinch we can match the hot stream should be higher, so that one with this one, yeah, this one with that one. So that's how we get to this graph, and then we can calculate how much then maximum heat that we can transfer. Yeah, make sure that the temperature doesn't violate your delta T mean, and then you can calculate the temperature outlet. For example, in this case 180, this is then you maximize until 150, while this temperature is 117.5, so you will need another heater over here, or if you can then use some of the heat extra coming from this stream, heat it that, and then the remaining you can then use hot utility, and then to get to 135. So that's what I did over here. So this is like an option, yeah, an option. To recap, I think I need to recap very quickly. So you have the base case design, as in this case. Where's that stuff? Sorry, yeah, I'll take another some minutes. Where's that stuff? So this is your base case, right? You know the load, and then you can then calculate. You can design the heat exchanger accordingly, and then you can then calculate the capex, and then calculate the opex based on the load, and then you can then put the number here in this table, right? And then you designed an improved one. So say for example you design only this heat exchanger, for example, yeah, and then you can then calculate the opex and capex, and then put that as an option one, and then you can also use, yeah, you can then split this into another design. Say for example option one is only using this heat exchanger network, and option two you can then apply these two exchangers, and option 3 you can then apply these 3 exchanger, and then option 4 you can apply these 4 exchanges, right? So that's options that you can then use in your economic calculations. So you have like 1 2 3 4 options plus 1 with the base case, and then you can make this type of table, and then calculate the hot cold utility respectively, and then investment required and the operating cost. Put operating cost over here, and then you can then present this, and then propose which design is the best in terms of the capex and opex. So for example, this is the base case, and this is then the proposed optimum case to be yeah, proposed or as a result of your study. So I think that's what I want to share. We are over time by 2 minutes. Take home messages: be careful with your data. Yeah, make sure that you have reconciled make sure that you have reconciled your mass and energy balance. It has to be balanced, and then you need to understand your process inside out. See where you can modify your process in such a way that you minimize your hot and cold utility from the external, and then yeah, you only do most process modifications only if it benefits you. Yeah, sometimes you can then, well, if we can reduce the pressure of the column here and there, maybe we can reduce the energy required, but then it may save you or it may not save you. Something that you have to evaluate yourself. And then lastly, then you can then make this table to evaluate and yeah, to visualize your options, so that people can then understand why you pick a certain design over the other. So with that, I think I